starting Chapter 2 of the Network Plus certification class. Remember, we're using Mike Meyer's CompTIA Network Plus Guide to Managing and Troubleshooting Networks, the 5th edition, for exam N10-007. So Chapter 2 is a discussion of network topologies and some cabling. So when we talk about network topologies, so when discussing network topologies, we're discussing two things. The physical network, that's how devices connect to each other, along with the logical topology, which is how the network device thinks it's connected to the network, what type of it perceives, what's it look like. In some cases, both the physical and logical topologies will match, but in others, the topologies don't. In this chapter, we're going to discuss 5 physical topologies: the bus, the ring, the star, the mesh, and hybrid. Bus and ring being the oldest technologies, really not used that anymore. The star is probably the most commonly used topology today. The hybrid is another commonly used topology, and our mesh, which is very rarely used except for very specific use cases. In the bus network that we're going to discuss, and the reason it's not used anymore is because it's very old. It was probably the very first physical topology that was in use in modern networks, what could be considered a modern network, and it used coaxial cable. There were 2 types of coaxial cable it used, and depending on the type of cable you used, you could either get 185 meters in distance or 500 meters. The network was a half duplex technology, so when we talk half duplex, we're saying one device on the network can transmit at a time. So one device transmits, the other devices receive. When the first device finishes its transmission, its Ethernet frame, another device could then transmit its frame. So only one device at a time. Everyone else was listening. This coaxial cable was terminated on both ends by a resistor. That termination was called a terminating resistor or a terminator. One end was grounded. That grounding prevented signal reflection. So when the cable reached the end of the cable, the signal reached the end of the cable, didn't reflect back on the cable, causing interference. Coaxial cable is very resistant to electromagnetic interference, or EMI. EMI is a term you'll hear throughout networking. It's unwanted signal introduced to a copper cable from an outside source. For example, microwaves, fluorescent lighting, motors, they're all sources of EMI. And the coaxial cable is actually very resistant to that. So this is what our bus topology looked like. It was a long piece of cable, terminated at both ends. One end was grounded. The network devices in this diagram, PCs, would tap into that network. Sometimes they would actually tap into it with something called a vampire tap. In other cases, we'd insert a PC, a pigtail into the network using a T adapter. Our ring networks were a ring where the network devices were actually inserted into the ring. It was circular in nature, so you started at one device, and the cable went from device to device to device and ended up back at the original device. So everything was in a ring. No cable termination was required. The token in this ring environment actually traveled from device to device in a counterclockwise motion. Ring networks, you can find they're rare, but you can find them installed in fiber optic networks in locations. It's very rare and usually only used in wide area networks or maybe large campus networks. So this is what a ring network looked like. The token was passed from device to device. The way this actually worked was, we'll see in this case, the PC at the bottom of this diagram had the token, and it would send that, it had a message to send, so it would send the token in a counterclockwise motion to, in this case, the printer that sits next to it. The printer may or may not have needed that information, but that token was then passed from PC to PC to PC back to that server, and then made its way back to the original PC. That token was never released until it got back to that PC. At that point, the PC would release the token, seeing that the message was delivered, and pass the token to the next device. If the next device had data to transmit, it would do the same process. It would attach the information and send the token all the way around the ring until it got the token was returned. And that process would happen over and over again. The biggest problem we had with the ring and bus technologies was a cable break. So if a cable broke in the system, the entire network would go down. So it was a huge problem. In the ring technology and some fiber optic networks, they developed a self-healing technology. But again, this is a specialized network device, and it's not used in day-to-day business networks. Still talking about our physical topologies, next is our star. In a star, we have a central box. You can call it a concentrator over the first devices in this star topology. But it was a central box where all the devices connected individually to the box. The advantage of the star topology was that if one cable broke, the only device affected was the device that was attached to that one cable. If the central box failed, the entire network failed. This is kind of what a star network looks like. Keep in mind, this is the most common network we have in place today in terms of a physical network. That central box in the early Ethernet days was a hub. In today's network, those are switches. But you have your central box. In this case, in today's modern network switch, would go from that switch, and each cable would go to a single device on the network. A mesh topology. This topology is where every device connects to every other device in the network. This can be very expensive. It's extremely fault tolerant. It's really not useful for most applications and most networks, just due to the cost. Here's what a mesh network looks like with just 5 devices. Notice every device connects to every other device. If there's a cable break anywhere in here, anything can be rerouted. If a device goes down, traffic gets rerouted. Extremely fault tolerant, but extremely difficult to manage, maintain, and install, and very, very difficult to grow. If we add a 6th device into this network, see what happens. So adding the device gets very expensive and very complicated. Mesh networks tend to be relatively small, and they're used only where extreme redundancy is critical. In most cases, we can use a hybrid technology, which may have a partial mesh at its core, and then a star network at the periphery. So in our hybrid topologies, our critical links we try to mesh or put as much of a mesh together as we can. Our less critical links usually are in a star or maybe some other topology. Again, our important links are fault tolerant, while less important links use a far less expensive technology. So in this diagram, the routers, which are the circles with the arrows, they are a core of the network, and they're extremely important to this network, so they are connected in a mesh. The other 3 locations or 3 facilities are connected in a star type fashion. 5 physical topologies, but in the logical topologies, really just centered around a logical bus or a logical ring. The logical bus emulates an Ethernet network, and a logical ring emulates a token ring network or a ring network. In these logical topologies, we're usually a physical star. In fact, so physical star, logical ring, physical star, logical bus. So in our logical bus topology, at the center of our network is a device called a hub. It looks a lot like a switch. If you walk, in fact, you cannot buy a hub anymore. These hubs are no longer made. You can buy them on eBay and at some used computer shops, but hubs are no longer manufactured. It looks, an Ethernet switch looks a lot like a hub. The reason you can tell this is a hub, it actually says Ethernet hub on the device. This is a layer 1 device. It would be our central wiring closet, and again we have a bunch of devices come to it, so it's a physical star, but because it's a hub, it's a logical bus. It's a physical star, logical bus. So in a ring network, or a token ring network, we had this media access unit that sat in our wiring closets. Again, it was a star. Each individual cable would come in and plug into one of these 8 ports. Physical star, but it was a logical ring. This device acted as a token ring. It would actually send the token through each of those ports in a ring type fashion. So that's the discussion of our logical and physical network topologies. Again, remember, most networks today are physical stars, but we do have the 5 types. We have the physical ring, the physical bus, the physical star, physical mesh, and our hybrid. In the logical side, we have a logical ring and a logical bus. For cabling, we're going to discuss largely 3 types of cables today. The first is our coaxial cable. This is an older technology. We don't use this very much anymore. In fact, the only place you'll find coaxial cable used today is in residential cable modem installations. You will not find a coaxial cable in a modern business. That said, you may encounter this question on an exam somewhere, and it's a good idea to know what this is. The coaxial description is a central conductor surrounded by insulation. The insulation is surrounded by a metal shield, and it's all wrapped in a sturdy jacket. The advantage of coax is distance, again up to 500 meters. It offered very good protection against electromagnetic interference, or EMI. And here's a discussion of EMI here, I'm not going to go into it. But EMI interferes with signals being transmitted across that copper wire, so EMI can cause problems in a network. And coaxial cable did a pretty good job of protecting against EMI. You could run, it was not unusual to see these run up elevator shafts and factory floors. Twisted pair cable is the cable type most often used in networking today. Each pair of conductors is wrapped around each other in a twist, and of the 4 pairs, each pair in that cable has a different number of twists per inch. This helps reduce crosstalk among the cable pairs. We have 2 types of twisted pair cable: unshielded twisted pair, that's the most commonly used today, and shielded twisted pair. Twisted pair cables are terminated in the walls on a wall jack and in a wiring closet in a patch panel. Patch panels and wall jacks are terminated with an RJ45 jack. Another term you'll hear for that jack is an 8 position, 8 contact, or 8P, 8C jack. This is a picture of some unshielded twisted pair cable. The UTP cable has very little protection from EMI, so you got to be careful when you install this. You want to avoid running this over fluorescent lights, near motors, avoid microwaves, refrigerators, that type of stuff. Keep this stuff in conduit and keep it away from those EMI sources. It's very inexpensive to purchase and install. You can get 1,000 feet of this cable for under $100 at most cabling contractors. It's very easy to work with. It comes in two types, a solid core and a stranded. The solid core is run in our walls. That means it's run between the patch panel and the wall jack. The stranded core is used for our patch cables. The maximum distance we can run from a network device to our switch or a central location, that electronics, from electronic device to electronic device, is 100 meters. So from PC to switch is 100 meters. From switch to server is 100 meters. Shielded twisted pair, again, is a lot like same. It's the same cable as an unshielded twisted pair, but we have a foil wrapped around it, and that foil actually provides some protection from EMI. So this is a little bit better, provides better protection against EMI. It is thicker than the standard UTP cable, and so because it's thicker, you're going to get less cable in a conduit. So we typically run our cables in walls and conduits. So we'll say you have a 2-inch conduit, you might be able to get so many pairs, so many cables of unshielded twisted pair there. If you try to put shielded twisted pair in that same conduit, you'll get less cable in that, so you'll need a bigger conduit. It's a little bit more difficult to work with the foil, but it's not that bad, and it is more expensive than unshielded twisted pair, primarily because we just don't use it very often, so they don't make manufacturers much of this. Within our twisted pair cabling, we have different categories or different types of cable, and those different types are called categories. The categories are categories 3, 5, 5E, 6, 6A, and 7, and the maximum bandwidth they support is as follows. Category 3 supports up to 16 megabits of bandwidth. We don't find Category 3 around very often. It's usually in very old buildings and it's legacy. Category 5, again, is another older one we just don't use very often. In fact, we don't use it at all anymore, but again, you'll see it in some older buildings. That supports up to 100 megabit per second network connection. Category 5E, a lot more common than 5. Supports up to 1 gigabit. Again, you'll find a lot of 5E out there. Category 6 supports up to 10 gigabits. There are some distance discussions we'll have at a later chapter. 6A supports up to 10 gigabits at 100 meters. And Category 7 can support more than 10 gigabits. With fiber optic cable, we can transmit light, not electricity. There are two types of fiber optics used, single mode and multi-mode. Our single mode fiber uses lasers, our multi-mode uses a laser LED. Because this transmits light and not electricity, fiber optic cable is immune to EMI. Remember that fiber optic cable is the only cable immune to EMI. All other copper cables, even if they're shielded, can be affected if the EMI source is strong enough. We're capable of going very, very long distances with our fiber optic cable. A single mode fiber run can go up to 10 kilometers. And our fiber is made up of 4 different components. We have our core, which is the medium where the light, that's the actual glass where the light travels. Cladding, it helps keep the light within that glass core. Buffer adds strength to the cable. And our jacket holds everything together. When dealing with fiber optic cable, especially for installation within walls, use certified professionals. This is extremely difficult to terminate and do it properly. You want to have your fiber optics, again, terminated properly, and you want it done by professionals. Also, installing fiber optic cable can be hazardous due to the small size of the fiber optic core. If that thing were to get into your bloodstream, it can actually cause damage, and it can fit in capillaries. So these glass pieces are very, very thin. Always have a professional install your fiber optic cable. Fiber optic cable can be identified by sizing of its core and cladding. So it's core size over cladding, and it's measured in micrometers. So common sizes for fiber optic cable. Single mode is 8 to 10 microns of core and 125 microns of cladding. In multi-mode fiber, we have two types of multi-mode fiber. One is 50 micron cores, 125 micron cladding, and 62.5 micron core with 125 micron cladding. The 50 micron is actually more modern. It's used in current networks. The 62.5 micron you're going to find in older networks. It's kind of legacy. When working with multi-mode fiber, keep in mind that 50 micron and 62.5 micron fiber are not compatible. If your fiber installation has 50 micron fiber, and one way to know if it's 50 micron fiber, if the fiber is not labeled, if you find out how it's designated. OM2, OM3, OM4, and OM5 cable are all 50 micron fiber. They are not compatible with 62.5 micron patch cables. 62.5 micron fiber is called OM1, and that is not compatible with the 50 micron patch cables. So, single mode fiber has a core size of 8 to 10 microns, and it's all compatible with each other. When you order single mode fiber, you just simply order single mode fiber and someone comes and installs it. It can range from 8 to 10 microns, and all of that is compatible with all patch cables. When you're talking about a single mode fiber, one of the reasons we can get a long distance out of this is the fiber is using an actual laser, and it transmits that fiber, that laser beam, down the center of that core. And we can get long distances out of this fiber optic cable, again up to 10 kilometers. For multi-mode fiber, the fiber uses an LED, and the signal actually travels along the outer edges of that core. Because the signal travels along the outer edges of that core, we end up with a possible problem called modal distortion. This is when your light arrives at different times from the beginning to the end. So modal distortion is really prevalent along long distances, so we tend to use this in multi-mode fiber and at short distances of 500 meters or less. Again, remember, fiber optic cable uses light for the transmission of the data, and we have two different types of cable, multi-mode and single mode. In multi-mode, our light is at 850 nanometers. With our single mode fiber optic cable, we have two different wavelengths. We can either use 1310 nanometers or 1550 nanometers. In our twisted pair cabling, remember we had the RJ45 jack, which is a fairly common jack. The only jack you'll see in twisted pair cabling. With fiber optics, we have three real common ones in the ST, SC, and LC, and one less common on the MTRJ. The ST connector, you're not going to see that in more current cable plants. Anything done in, say, the last 10 years is going to use an SC or an LC. You just don't see the ST used much anymore. The MTRJ, again, that was something you saw in older cable plants. Again, we don't see that used very often. Two other technologies we have in networking that you should be aware of is serial. This uses an RS-232 cable with a DB9 connector. A lot of manufacturers use this serial connection to configure our console ports. So we plug this into a console port. We can then go in and configure our device for initial configuration. And after that, we can browse to or SSH or Telnet in some cases to our device and configure the rest of it online. Our network cable, our serial cables, are limited to 56 kilobits per second. And again, we don't use this for networking. It's used for configuration of initial configuration of our devices. There is also an older parallel networking capability used to connect two devices together in a point-to-point connection. It's the parallel cable. The specification is done by the IEEE in 1284. Again, we don't use this in modern networks, and this is also limited to about 2 megabits per second. When running cable, the term you'll hear in sometimes is plenum cable. Plenum cable is used when we're going to run our cable near a heat source. Two organizations you'll hear in networking, especially when talking about cable and layer 1 and layer 2 networking, is the Institute of Electronic and Electrical Engineers, or the IEEE. The IEEE is responsible for creating and updating specifications for Ethernet and other networking topologies. The 802 subcommittee creates our standards for our frame types. The Telecommunication Industry Association and the Electronics Industry Association, the TIA and EIA, is responsible for defining cabling standards. The EIA is no longer around. They actually stopped functioning as a governing organization probably 10, 12 years ago. The Telecommunications Industry Association actually took over for the EIA. But you will see a lot of the specifications marked as TIA, EIA, because the EIA actually set these standards a long time ago, and the TIA just adopted those standards and will move on into the future, developing future standards.